a knowledge-driven approach to adaptive assistance using preference reasoning and explanation. I'm Willie, and my co-authors are Leilani Gilpin and Irina Rabkina. Let me present this scenario to you. We have a person who needs to organize their medications. Now, this can be an arduous task for some people who have to take, say, 5 to 10 pills a day. We've been looking at how can a social robot assist a person as they organize the medications for the week. The robot observes as they place the pills into a sorting grid such as this. We have the different days of the week, and the rows here are times of the day: morning, noon, evening, and night. So the person begins, say, placing all of their morning vitamins. All right. Now that they've placed all the morning vitamins, next the person is going to organize their levodopa. Now, levodopa is a dopamine agonist that a person with Parkinson's disease may take so that their brain will produce the necessary dopamine to allow them to do a physical activity. So a person may take this before any sort of planned physical activity. Now, how long they take it before the physical activity can be a matter of personal preference. So the person places the pill in the morning position. The robot sees this and thinks, this isn't quite right. So it interjects, try removing a levodopa from Wednesday. And the person, quite confused, wants to respond, why? I prefer to take my levodopa a few hours before any planned activity. So how does the robot answer this question? How does the robot adapt to the user's preference? So the problem that we're looking at is, how can we have a social robot that's able to provide some sort of assistance while managing household activities such as managing medications? And important in this is that we want the robot to be able to adapt to the user preferences. Also, the robot needs to be able to provide some sort of explanations. And these explanations can serve a couple of different purposes. One is it can be used to educate or inform the user. If a person's taking 5 or 10 medications a day, it can be very hard to keep track of what all of the different constraints and rules for each medication. But also it can serve to help build the trust and confidence in the robot as a tool that can help assist with the daily activities. So our proposed architecture consists of 3 components. The preference reasoning component is responsible for determining what preferences the user has. This preference is passed to the adaptive assistance component. Now, the adaptive assistance component uses this preference along with perceptions that it takes, its observations of the task that the person's performing, along with any social cues such as language or eye gaze that the person may be using. Now, based upon these preferences and the observations that the robot has made, it determines what is the right type of assistance for the robot to provide. Along the way, it produces a plan, where the plan is what's the sequence of actions that the user needs to take in order to complete the task. So finally, we have the plan, which is the plan for the user. Also, we have the user's preferences, and then this gets fed to our explanation component. So finally, the explanation component uses the plan and the preferences to generate an explanation, using common sense knowledge to fill in the blanks of the reasoning, provide some additional justifications. I'll briefly walk through each of these components. In order to adapt to a user's preferences, we need to know what those preferences are. Now, we consider 2 different types of preferences. The first is a task preference, indicating how the person prefers to perform the task. For example, one person may prefer to organize their medications of one type at a time. So they do all of, say, the morning vitamins. And then they go and proceed with some other medication type, perhaps placing all of their blue pills, perhaps their levodopa. Now, another person might have a different preference on how they want to do this. They might do it, say, one day at a time. So they do Sunday, then they place the pills from Monday, then Tuesday, so on and so forth. Now, both of these approaches are valid, and they're likely to result in the same outcome, the difference being really a matter of preference. Now, the other type of preference really has to do with perhaps actually altering the outcome. All right, so perhaps one medication is going to have a rule saying it must be taken before a meal or with a meal, let's say. All right, so if it has to be taken with a meal, A person could say, oh, I can take this with breakfast. I can take this with lunch. I can take this with dinner. Any of those perhaps are acceptable. Now we're looking at another type of constraint that says, oh, you have to take this before some sort of activity. Now, how long before that activity you take it, again, can be a matter of preference for what works for that person. Now, there's a few different ways in which the robot might be able to go about reasoning about these preferences. Now, one possibility is that the person tells the robot what its preferences are, right? So the person just says, I prefer to take my levodopa a few hours before any planned activity. Now, using some NLP, we could interpret this into some sort of representation that the robot is then able to understand. Alternatively, we could also do this through inference by observing the person's behaviors, their current behaviors and their past behaviors, and be able to come up with some rules or maybe use some analogical reasoning to determine what are the person's preferences. In other work, we've used analogical reasoning and an analogical theory of mind to be able to recognize a person's goals and preferences based upon observations of their actions. To provide adaptive assistance, we want the robot to be aware of the user, their preferences, and their progress in the task, also any sort of subtle social cues they might be using. All right, so we have the person has laid out all of their pills for the morning, and then they go ahead and place the levodopa. And at this point, the person perhaps erroneously placed the pill here. Perhaps it should go in the time slot after it. Now, in our previous work, we've used the hint engine to be able to recognize these sorts of misplacements. For the hint engine, it's going to take 3 steps. So the first step is to estimate how much need for assistance does this person have. The need for assistance can be based upon making a mistake in a task such as this. But just because they've made a mistake doesn't mean that you necessarily want the robot to interject. Right? Perhaps the person wants to be able to figure it out for themselves, and you don't want to be overstepping and being constantly giving assistance. So the robot is also going to observe other sorts of cues, looking at their eye gaze and be able to sense what kind of language are they using to indicate really how much need for assistance does the person have. Once the robot does determine that the person does need assistance, it's going to then figure out, okay, well, what type of assistance? All right, so the second step is to find the appropriate action. And to do this, we generate a plan, and the plan is going to be, these are the sequence of steps that the user must take in order to complete the task. And now the robot then will take the first action in this, first action being the remove pill, and so then it's going to look up what are the types of ways in which the robot can assist on a task like this. So given how much need the person has, given the type of action that the user needs to perform, the robot will have a series of assistances that it can provide. And then this will result in some sort of natural language output, such as, try removing a levodopa from Wednesday. Now, there's a lot of different ways in which we can use user preferences to adapt how the assistance is given. Right now, we're really just looking at in the plan generation. So here we have a preference for how long before a given activity does the person prefer to have their levodopa. And so the plan that gets generated is based upon this preference. Now, explanations are usually built in the form of expert explanations. How does how does perhaps the robot designer understand what is going on? So instead, we want to develop a common sense explanation that also justifies the agent's behavior by supplementing their decisions, right? So we have some common sense that creates a causal chain of reasoning. So the explanation process begins by querying our common sense knowledge base, ConceptNet, and we use the key terms from the plan that was generated by our adaptive assistance component. So once we've queried for these key terms, we have some facts. And we need to start finding connections between these facts. And we're finding connections through some common terms. So we're going to construct a chain of reasoning. So we have all these different facts, and we start finding these connections between them. And finally, we're going to deduce this down to a clear, concise explanation frame that has the key facts that explain why the robot has given its explanation. Now, in future work, we'll take this explanation frame and apply some template natural language generation so that the robot can actually then finish this and say, well, you prefer to take your pill before any activity, and you have an appointment at 1 p.m., thus providing the user with an explanation of why the robot gave the assistance it did, but also an explanation that is relevant to the person's preference. So let me walk through this whole thing now, and to give you a sense of how our components are working. Okay, so really now before our system starts, we're starting off with an assumption that the user has already provided their preference, whether it came through natural language or however it may be. We start off with this preference that the person has. All right, so after this, the person now is going to sit down and start to execute the task. And so they begin by placing all their pills, and they place all their morning pills just as we've done before. And then they go ahead and place the pill in the afternoon, their levodopa pill in the afternoon. And at this point, the robot observes this and realizes, that was perhaps a mistake. That should have actually been in the morning time slot and not in the afternoon time slot. If the robot believes that the person needs assistance at this time, not just because there was a mistake, but because of some other sort of social cues, the robot might then interject and say, try removing a levodopa from Wednesday. Again, perhaps the person might be confused by this and asks, why? And so the robot takes this question, right? When we're not actually processing any natural language processing here, but we say that the next thing that the system can do is that there's the explanation component will take the plan, take the user preferences, construct this explanation frame. From this explanation frame, again, our system ends here, but our explanation frame, we would be able to use some natural language generation, some template-based natural language generation to construct this sort of output saying, well, you prefer to take your pill before any activity, and you have an appointment at 1 p.m. So this is a proof of concept, and it's intended to demonstrate how these components can be used to solve a really important problem. But there's a lot of next steps that we need to take. One really important challenge is that all of the components that we're working with here are actually based upon very different representations. For example, our analogical reasoning and our preference reasoning all uses NextKB, which is based on a psych ontology. Meanwhile, our explanations are using ConceptNet. So we need to work to get all of these onto a common representation, which is no easy feat. Another important step is to allow the robot to make inferences about the person's preferences based upon observations. Again, we've done this in some other work, but we're looking at how do we adapt that work to apply to this sort of domain. Also, something else that's really interesting is that when we generate a plan as part of the adaptive assistance component, we can generate some counterfactuals based upon different preferences that a person could possibly have. And we're starting to look at how can we use these counterfactual plans to generate some sort of better explanations why the robot is giving the assistance it is. So lastly, perhaps the most important is to close the loop. All right, so we'd like to allow the user to provide some feedback after the robot has given an explanation. Now, this feedback can be used by the system to improve any of the components, right? So, for example, the person may indicate that their preference is different in a particular context, right? So maybe in general, they want to take it a few hours before activity. However, maybe on Friday nights, they don't want to take it too early. They'd actually prefer to take it a little bit later. Also, the person could suggest that the explanation was not clear enough, right? And this could also then be feedback to our explanation component, allowing that component to produce a better explanation. Overall, our main contribution is a demonstration of a knowledge-driven architecture, right? Each of these components are knowledge-driven. And together, these components can allow a robot to adapt. It adapts the type of assistance it gives based upon its observations, based upon preferences, and it's able to give explanations that are specific to the person and their preferences. Thank you.